We've talked at this point about the quantitative use of the chemical equation, how it allows us to relate multiple different substances to each other and relate their masses through going using the molar amounts and the molar equivalencies and converting between mass and moles using the molar mass, even converting between moles and molecules, etc. Now we come to an extension of that that is vitally important, and that is the concept of limiting reagents. Whenever we have a reaction that we set up in the real world, we rarely have perfect stoichiometry or perfect ratios of the 2 or 3 starting materials. And when we do not have perfect stoichiometry or perfect ratios of those reactants, what happens is that one reactant will be consumed before the other reactants are. And what happens is that any reaction stops as soon as any one of the reactants is totally consumed. Let's do a practical example of this. If we go and revisit this burning of hydrogen with oxygen that we've seen even back to chapter 1, we see that on the molar level, with the balanced chemical equation, there's 2 moles of hydrogen gas react with 1 mole of oxygen gas. Well, let's take a scenario where before the reaction began, we had 10 moles of hydrogen and 7 moles of oxygen gas. As we do the reaction, what we will notice is that if we consume all of the hydrogen gas, we've only consumed 5 moles of the oxygen gas. And as a result, what we have left over is 2 moles of oxygen gas that we haven't used. Now, the reaction stops at this point, however, because we have no more hydrogen gas. So even though we have excess oxygen, we have no more hydrogen. And so this terminates the reaction. The important thing to note from all of this is, after a couple of definitions here, first, the reagent that runs out first is known, not surprisingly, as the limiting reagent or the limiting reactant. And the other reactant or other reactants are known as excess reactants. What is vitally important in this discussion is that we must base stoichiometric calculations on the limiting reagent. If I was asked in this reaction, how many moles of water are going to be produced? Well, if I base the calculations off of the number of moles of hydrogen gas, I would say, well, there's 2 moles of water for every 2 moles of hydrogen gas, so that's a 1-to-1 ratio. So if I start with 10 moles of hydrogen gas, I should end up with 10 moles of water, which is what we see. However, if I based my stoichiometric calculations on oxygen instead, then if I didn't account for the limiting reagent, I would say, well, I have 7 moles of oxygen gas to begin with. So there's 2 moles of water for every 1 mole of oxygen gas. So if I started with 7 moles of oxygen gas, I must produce 14 moles of water. But in reality, I only produce 10 because I run out of hydrogen first. So that's why it's absolutely necessary to first figure out what the limiting reagent is, and second, base stoichiometric calculations only on the limiting reactant and not on the amount of the excess reactants. Let's do a couple examples. First example is the Haber-Bosch process. It's an extremely important industrial process, makes more than 175 million tons of ammonia every year, and ammonia then is used in many fertilizers. And it's this simple reaction. You take nitrogen gas and react it with 3 moles of hydrogen gas, and you produce 2 moles of ammonia. So the question is, how many moles of ammonia can be formed from 3 moles of nitrogen gas and 6 moles of hydrogen gas? So I have 2 different reactants and amounts for each. The very first thing I need to do is determine what the limiting reagent is. That's step number one, determine the limiting reagent. How do I determine the limiting reagent? Well, first I look at the ratios between my different reactants. So here I can say that 1 mole of nitrogen gas is equal to 3 moles of hydrogen gas. That's the molar equivalency from the balanced chemical equation. Then I will take the given amounts of one of those starting materials and figure out how much from that given amount, using the molar equivalency I just showed, how much of the other starting material would be required to react with all of the first material. And when I've done that, then I will compare whether the amount that I calculated is more or less than the amount that I actually have of the other starting material. So in this case, I'll take my amount of nitrogen, 3 moles, that's what I've been given, and I'll determine using the molar equivalencies, I'll figure out how much total, how much hydrogen gas would I need to react with that amount, with the given amount of nitrogen gas. And I come out with some value just using my normal unit conversion process. So here I come out with, what it tells me is I need 9.0 moles of hydrogen gas to react with all of the 3.0 moles of nitrogen gas. Now I take this value that I've calculated and I compare. Is this more than the amount that I actually have or less than the amount that I actually have? If it's more than the amount that I actually have, as it is in this case, then I know that hydrogen must be the limiting reagent because I need more than what I actually have. If this value is less than what I actually have, then it must mean that hydrogen is an excess reagent because I have more than what I actually need. And thus it's not the limiting reagent. Nitrogen must be the limiting reagent in that case. Now in this present case, the amount that I need is more than the amount that I actually have. And so hydrogen then must be the limiting reagent. Now, having figured out the limiting reagent, I can ignore the amounts of the excess reagent and only base my calculations on the limiting reagent. Since hydrogen is my limiting reagent, I'm going to base my calculations off of the amount of hydrogen to figure out the amount of ammonia. So my relationship here between hydrogen and ammonia is 3 moles of hydrogen is equal to 2 moles of ammonia. And then I use that as my molar equivalency and my conversion factor. I take my 6 moles of hydrogen gas, I put my conversion factor with the moles of hydrogen on the bottom so that it cancels and leaves me with moles of ammonia on top. I simply multiply through and divide, and I come out with 4.0 moles of ammonia. Now there is an additional concept here, which is known as the theoretical yield. The theoretical yield is the amount, and it could be in mass or it could be in moles, depends on how we want to express it, but it is the amount of product that's calculated using the amount of the limiting reagent. The theoretical yield is simply the maximum amount that we would expect to get from a reaction. How much should I get of product based off of the amount of limiting reagent that I have? Now, in many cases, the actual yield, this is what you actually isolate from a reaction, is always less than, or sometimes equal, if it's perfect, equal to, but in 99.99999% of the cases, your actual yield will always be slightly to a lot less than your theoretical yield due to any kind of process which may lose even the smallest amount of product. So we have an actual yield and we have the theoretical yield. How is it useful then to report values? Well, this is where we come to something known as the percent yield. The percent yield is simply an expression of, okay, how much of what we should have got did we actually get? And we take the actual yield, divide it by the theoretical yield, and multiply by 100%. That's how we report percent yields for reactions. Let's do a second example here and marry in this concept of percent yield and theoretical yields. So adipic acid is a material that's used to produce nylon, and it's made commercially by reacting cyclohexane, which has the formula of C6H12, and reacting that with oxygen in this following reaction. So we have 2 moles of cyclohexane reacting with 5 moles of oxygen to produce 2 moles of adipic acid and 2 moles of water. So the first part of this question is, if we have 25 grams of cyclohexane and 25 grams of oxygen, what is the theoretical yield of adipic acid in grams? Essentially what we're asking is, how much adipic acid should I generate if I start with 25 grams of cyclohexane and 25 grams of oxygen? Well, the very first question is, which of those 2 starting materials is the limiting reagent? Which of those 2 starting materials do I base my stoichiometric calculations on? Well, in this case, I'm given the amounts in grams, not in moles. So what I need to do is I need to convert the mass values that I've been given into moles, then choose one of those starting materials, and using the stoichiometric, the molar equivalency from the balanced chemical equation, saying that 2 moles of cyclohexane is equal to 5 moles of oxygen, take one of those starting materials and calculate how much of the other starting material I would need. And then I compare my calculated value with the actual value that I am given. Let's go through that process. So 2 moles of cyclohexane is equal to 5 moles of oxygen, as we said from the period, just from the balanced chemical equation. So I need to convert both mass amounts to moles so that I can use this molar equivalency. So I take the mass of cyclohexane, I add up the individual atomic masses to get my formula weight or my molecular weight, which I can get in my molar mass then from that in grams per mole. And I put grams on the bottom, moles on top, and the grams cancel, and I come out with a certain number of moles of cyclohexane. I'll do the same thing with oxygen with its molar mass, and I come out with another amount of oxygen in moles. Now we will take one of those starting materials and figure out how much of the other starting material I would need to react with all of that, simply using the molar equivalencies that I've been given. So I do this, I'll start with cyclohexane, I took the amount of it, and using the molar equivalency conversion factor, I then figured out how many moles of oxygen I would need to react with all of the moles of cyclohexane. So this is now my calculated amount of oxygen that I need, and I compare that with the amount that I actually have. So I need 0.7440 moles, but I have 0.7813 moles. I have more oxygen than what I need. So oxygen must be the excess reagent, and cyclohexane must be the limiting reagent. Now that I've figured out that cyclohexane is my limiting reagent, I'm going to ignore the amounts of oxygen. I'm going to focus only on doing my calculations using the amount of cyclohexane. So now I would do my normal normal process for figuring out the amount of product from the amount of one starting material. So normal stoichiometric calculations. I figured out the number of moles of cyclohexane already. So now I convert that to moles of adipic acid using my molar equivalencies. It looks like it's 2 moles of cyclohexane to 2 moles of adipic acid. So it's a 1-to-1 ratio. And then I need to go from moles of adipic acid to mass. I use my molar mass for that, where I simply add up the atomic weights of each of the atoms in the compound. That will give me my molecular weight, which is my molar mass in grams per mole. In this case, I've canceled moles. I have moles of adipic acid on top, so I want to put moles of adipic acid on bottom to cancel that out, and grams of adipic acid on top. I multiply through, and I come out with a value here, 43.5 grams of adipic acid. Now you may wonder, why do I only have 3 significant figures in this case, whereas I'd carried more? I'd carried 4 significant figures as I was going through. And it's important when we're doing multi-step calculations. It is okay to carry extra digits in the process. You really want to avoid the possibility of introducing rounding errors. And so only round your number to the appropriate number of significant figures at the very end of the calculation. If you do it before that, you can introduce minute amounts of rounding error, which can then propagate as you go through a calculation. So we started out with only 3 significant figures in the mass of the cyclohexane, so we have to end with only 3 significant figures in the mass of adipic acid. Okay, so we answered part A. We figured out the theoretical yield of adipic acid in grams. Part B, we have an actual yield. We obtained 33.5 grams of adipic acid. That's my actual yield. So what's the percent yield? Well, the percent yield is simply the actual yield divided by the theoretical yield times 100%. So I simply take 33.5 grams divided by 43.5 grams, multiply by 100%, and I come out with a percent yield of 77.0%. And this is how we use limiting reagents to help us really keep track of mass in a chemical reaction.